In this video I am going to show you how to integrate by parts. In order to learn how to integrate by parts, you should already know the table of common integrals by heart, and you should know how to integrate using a substitution method. I have already made quite a few videos about integration, and I have in the description of this video some of the links of those videos which are going to be useful to you. I recommend that you watch them and solve some problems which I had worked through there. Let's now focus on integration by parts. The mascot of a problem solved by integration by parts is this integral. Integral of x e to the power x dx. It is obvious that this integral can't be solved by a direct approach or some easily thought of substitution. That is why integration by parts is an important method to know. It just powers through the problems like this one. It eats them for breakfast without breaking a sweat and then asks if there is more of these integration dissidents to be sacrificed to calculus gods. As always, when solving an integral, the first thing that needs to be done is determining the area in which that integral is defined. For this integral, it is easy to see that the area in which it is defined is an entire set of real numbers. Let me now introduce to you the integration by parts formula. So the formula is an integral of u differential of v is equal to u multiplied by v minus the integral of v differential of u, where u and v are some functions. I recommend that you learn this formula by heart, as it is something that you should know forever. All that this formula does is that it takes the integral you are working on and then it transforms it into this new and most importantly different integral that is easier to solve than the integral you had started from. Now when applying the integration by parts, you yourself have to choose what is the function u and what is dv. That is the trickiest thing to do when using this method, but I assure you that it is nothing complicated. There are some neat tricks to help you in making your choice, and I will later introduce them to you. The general principle is to pick one of the two factors you have in your integral and make that factor u. The remaining factor is dv. For you want to pick, and this is important, that one factor that becomes simpler when you differentiate it. The remaining factor will be your dv, unless that becomes more complicated when you integrate it. So basically, for you, you want to pick a factor which gets simpler or breaks down or gets smaller when you take the derivative of it. Basically, that means that the degree gets smaller, the factor decreases in the number of terms, or it reduces in some different way. So take that one to be u, and whatever is remaining is your dv. I understand that all of this sounds very confusing, so let me show you what I mean on this example of ours. The question here is which one of the two factors, x or e to the power x, gets simpler when you take its derivative. Well, the derivative of x is equal to 1. That is simpler. X has dropped down. It has a lower degree. The derivative of e to the power x is that same e to the power x. There is no change. It has not become simpler. That gives us a pretty good idea that u has to be x and that we should take for dv the remaining factor e to the power x dx. Unless e to the power x becomes more complicated when we integrate it, which it doesn't. The integral of e to the power x is just e to the power x. The important note here is that whichever factor you pick for dv, it also gets dx. So always connect dv with dx. This is perfect because we now have u and dv. And now we can plug this into integration by parts formula. Now, as you can see in this integration by parts formula, we know u and we know dv. So this is our known. That formula also needs v and it needs du. We don't know that, so we need to calculate it. We know that u is equal to x, so du is going to be a derivative of u multiplied by a differential of x. This is x prime dx, and that is just 1 multiplied by dx, which is dx. So we know that du is equal to dx. In order to find v, we are going to integrate the differential of v. That is an integral of e to the power x dx, and that is just e to the power x. I forgot dx here. When solving indefinite integrals, you remember that we have always wrote down that plus c constant at the end. We are not going to do that here. We are not going to do that when using integration by parts formula for calculating this v over here. The reason for that is because that plus c in this position is never going to have any effect on final solution that we get. If you don't trust me, write down that plus c and see what you will get for a final result. At this point, we have all the information that we need for integration by parts formula, so we can plug all of this into that formula. Let's use this formula on our integral. Remember, x is u and e to the power x dx is dv. So this integral becomes u multiplied by v, which in our case is x multiplied by e to the power x. And then we have minus the integral of v du. As you know, v is e to the power x and du is dx. Now that we have used the formula, you can observe the result which we now have. We have this function x e to the power x. There is no integral there. That is one part of our final solution. And then there is this integral of e to the power x dx, which is just a simple table integral. There is no problem for solving it. This is then equal to x e to the power x minus the integral of e to the power x dx is just e to the power x. And now we are going to add that plus c, where c is any real number, that constant of ours. So you see we add that plus c at the very end. Don't forget this plus c at the end because it is important. We have a final solution for our integral. As you can see, integration by parts is the method which made this integral solvable. The summary of integration by parts is that you first need to find your u, and then whatever remains is going to be your dv. Now, when you have found your u and you know what your dv is, you are going to find differential respectful of u, and you are going to integrate this to find your v. And the third and final step is to take all of this information and plug it back into the integration by parts formula. If it happens to you that you pick wrong u and wrong dv, the first time you try to solve an integral, it's important to not panic. It's just fine if it doesn't work out the first time. When dealing with integrals, volume is quite important. So the more integrals you solve, the better at integrating you will become. And make those mistakes. Enjoy finding them and making them right. That effort is what is going to make you better at this. Just remember that it's okay to suck first. It's okay not to enjoy something. You know, people enjoy doing things that they are good at. In order for you to become good at something, you have to suck at it first, and practice makes perfect. In time, you will become good at this, and then you will start enjoying integration. Now, if you really hate this essential, in my opinion, step, the step of just being wrong and being forced into finding your wrongs and making them right, then I have a neat little trick for you. something that everyone who does a large number of integrals notices by themselves, and that trick is easy to remember by its acronym called LAIATE. In this LAIATE acronym, your u from the integration by parts formula will be the first thing that you find among these letters, and dv will be whatever remains. Now L stands for logs. That is a natural logarithm, ln, or a general log. I stands for inverse trigonometric functions. This is something like arcus sine of x or cosinus inverse of x. Now A, that stands for algebraic. Now what is that algebraic? It is polynomials and the powers of x, like x, x to the power of 2, x cubed, and so on. T in our acronym stands for trigonometric. Those are functions like sine or cosine. And E stands for exponential. What is exponential? Well, e to the power x, or maybe 2 to the power x, or anything else like that. So the trick is to follow these letters in this sequence. You start with L and you move to I, A, T, and E. The first one that you find in your integral is your u. So in our integral x e to the power x dx, we have this x and that is algebraic. We have e to the power x and that is going to be exponential. In our LAIATE acronym, A stands before E. So we are going to take for u that A. A was x, so u is going to be x. So we have taken the x and everything that remains under the sign of integral is going to be dv. Let's now put this LAIATE trick to the test and solve some more integrals for practice. In my opinion, the hardest thing is to pick u and dv. So here is the list of integrals and let's practice on it picking u and dv. So the first integral on our list is x sine of x dx. When you are solving an integral, the first thing that you have to do is to determine the area in which that integral is defined. You can see x here. The function x is defined for all x's which are real numbers. The function sine of x is the one you have next. Sine of x function is also defined for all real numbers x. Well, that basically means that the area in which this integral is defined is set of all real numbers. That is our area where the integral is defined. Now the second step is to solve an integral. We have x multiplied by sine x dx. We can use our LAIATE trick here. We have x, which is algebraic. We have sine of x, which is trigonometrical. Now, algebraic comes before trigonometric. Remember, LAIATE trick. A is before t. So we are going to pick for u that algebraic part which we have in our integrand. So u is going to be x. Everything that remains, sine x dx, is going to be dv. Now remember our formula for integration by parts. U dv is equal to uv minus an integral of v du. U dv is this integral right here. We have picked u, x, and we have picked dv, sine of x dx. We know u, we have u, and we know dv. What we have here on the right side is v. We don't know v, and we have du. We don't know that. So we need to find those two things. Let's find du. Differential of u is going to be derivative of u respectful of x multiplied by the differential of x. Differential of x because that is the variable in this expression u, which we are going to differentiate respectful of the variable x. So this is then equal to x prime dx, which is just 1 multiplied by dx, and that is dx. So we have found that du is equal to dx. We have du in our formula. We need to find v, and v is just an integral of the differential respectful of v. So that is an integral of sine x dx. Well, what is an integral of sine x dx? This is just a table integral. This is negative cosine of x. Now we need to take all of this information which we have, that u is x, that dv is sine of x dx, that v is negative cosine of x, and that du is dx. And we are going to plug it right here into this formula of integration by parts. So we have this integral, this is this integral from the formula. So this integral is then equal to u multiplied by v. U is x and v is negative cosine of x. We have minus sign and then the sign of an integral. V multiplied by du. V is negative cosine of x multiplied by du is just dx. And now we have to solve this, and that will be the solution of our integral. So this is equal to negative x cosine of x plus an integral of cosine of x dx. This is just negative x cosine of x plus integral of the cosine x dx. This is a simple table integral. Its solution is sine of x. And now that we have come to the end of our integration, we just put in that plus c. A c is an arbitrary real constant. And this is our solution. So the integral of x sine of x dx is equal to negative x cosine of x plus sine of x and plus that constant c. And the area in which this is possible is the set of all real numbers. So this is our solution. Let's now solve the second integral on our list, x squared sine of 2x dx. Again, first thing is to find the area in which the integral is defined. X squared, as you know, is defined for all x's which are real numbers. Sine of 2x is defined for all x's which are real numbers. And that means that the area in which our integral is defined is an entire set of real numbers. So this is the area in which we integrate. And now that we know that, let's integrate. We can make things here simpler by applying the substitution that t is equal to 2x. That will mean that x is equal to t half, and of course differential of t will be 2 differentials of x. Of course, in our integral only dx appears, and that is differential of t half. Let's plug in our substitution. We get an integral of t half squared multiplied by sine of t, and dx is dt over 2. This is just 1 over 8 integral t squared sine of t differential of t. I did this substitution here because I don't want to carry over in my calculations this constant here too, which appears from the double angle in trig function. Of course, you can jump right to integration by parts. This substitution is not necessary. It's just useful in making the calculations simpler in the way that you don't have to pay attention to number 2. Now we can use our Layette trick again. We have in our integral which we are solving t squared, and that is algebraic. We have sine of t, and that is trigonometrical. In our acronym, letter A comes before letter T. So for our u, we are going to pick t squared, and for our dv, we are going to pick everything else that remains in the integral. If you recall the integration by parts formula, u dv was equal to uv minus the integral of v du. This integral here is our integral from the beginning. This one right here, as we have transformed it. So we have t squared for u and sine of t dt for dv. We now need to calculate du and we need to find v. So let's do that. Du is going to be t squared, the derivative of that multiplied by dt, and that is just 2t dt. V is going to be an integral of dv, and that is sine of t dt, which is just going to be negative cosine of t. When we return all of this into our formula for integration by parts, we get that this is equal to u multiplied by v, which is negative t squared cosine of t minus the sine of an integral, and under that sign we have v multiplied by du over here. So v is negative cosine of t multiplied by du, that is 2t differentials of t. And that is negative t squared cosine of t plus 2 integrals of t cosine of t dt. Now remember here that this integral is of u dv. We have an integral of t squared sine of t dt, and in front of this integral we have 1 over 8 as a constant. We have to carry out that constant until the end of our calculations. So this entire thing is going to be multiplied by 1 over 8, and of course we have that same multiplication here. We have to not forget that 1 over 8, as I almost did here. As now you can see here, we have an integral of t cosine of t dt which we need to solve. And again, this integral can be solved using the integration by parts, and we are going to do that again. We have a similar situation as before, only this time u is going to be t, because we have only t here, and the dv is now going to be cosine of t dt. Differential of u is going to be differential of t, and v is going to be an integral of cosine t dt, which is just sine of t. So this integral is equal to 1 over 8 minus t squared cosine of t plus 2. And now we have that formula uv minus the integral v du. uv is t sine of t, and minus the integral of v du is sine t dt. Well, this is then equal to 1 over 8 negative t squared cosine of t plus 2t sine of t minus 2 integrals of sine t dt. This is equal to 1 over 8, and of course, when we solve this integral, we are going to need to plug in that plus c. So this is 1 over 8 minus t squared cosine of t plus 2t sine t minus 2 multiplied by the integral of sine t dt, that is negative cosine of t, and at the end we are going to plug in that plus c, where c is a real number. If you put that plus c here inside the brackets to multiply it by this 1 over 8, 1 over 8 multiplied by c, where c is a real number, a real constant, that is just going to be another constant c1, which is also a real number. So it doesn't change anything to put that plus c after the bracket. And now to continue our calculation, this is equal to negative 1 over 8t squared cosine of t plus 1 over 4t sine of t plus 1 over 4 cosine of t and plus c. Remember the integral which we have started from. It is an integral of x squared sine of 2x dx. And we have introduced the substitution here and then continued with that t. We have here t, but we need to return it to be respectful of x, because we started from the integral which is respectful of x. So we are going to use that substitution that t is equal to 2x, and we are going to return it into the final result which we have gotten here. So this is equal to negative 1 over 8 2x squared cosine of 2x plus 1 over 4 multiplied by 2x sine of 2x plus 1 over 4 cosine of 2x and plus c. This is then equal to negative 1 over 8 multiplied by 2 squared, that is 4. So this is just 1/2 x squared cosine of 2x plus 1/4 multiplied by 2, that is just 1/2 x sine of 2x and plus 1/4 cosine of 2x and plus c. Of course, this c is a real number, and this is the final solution for our integral. Third integral on our list is an integral of 3x plus 1 multiplied by cosine of x half dx. Again, we have to find the area in which this integral is defined. 3x plus 1 is well defined for all x's which are real numbers, and cosine of x half is also well defined for all x's which are real numbers. And that means that the area in which this integral is well defined is an entire set of real numbers. In this integral again we have algebraic 3x plus 1 and we have trigonometrical cosine of x half. Again, using the Lyate trick, we know that u is equal to 3x plus 1 and that dv is equal to cosine of x half dx. Differential of u is going to be 3dx and v is going to be an integral of cosine x half dx. So we are going to introduce the substitution here that t is equal to x over 2, and that means that the differential of t is 1/2 of the differential of x. Differential of x is 2 differentials of t. So this integral then becomes 2 integrals of cosine t dt, and that is just 2 integrals of cosine t dt. That is a table integral and it is sine of t. This is just 2 sine of x half. So the integral which we had started from now gets transformed by the integration by parts formula into 3x plus 1 multiplied by 2 sine of x half, that is u multiplied by v, minus the integral of v multiplied by du, that is 2 sine of x half multiplied by 3 dx. So this is equal to 3x plus 1 sine of x half minus 6 integrals of sine of x half dx. Again, we are going to introduce the substitution that t is equal to x half, and that will make dx be 2 dt's to solve this integral right here. So this is then equal to 3x plus 1 sine of x half minus 6 integrals of sine t dt, and we have to multiply that by 2 as we have these two here. So this is 2 3x plus 1 sine of x half minus 12 multiplied by this integral is negative cosine of t, and plus c, as we have no more integrations to do. So this is 2 3x plus 1 sine of x half plus 12 cosine, and t was x half, so we are going to return that substitution, and plus the real constant c at the end. Let's now solve the fourth integral on our list, x cubed ln of x dx. The area in which this integral is defined is x cubed, that is well defined for all x's which are real numbers, and ln of x, that is defined for x's which are strictly larger than 0. Our integral is defined inside the intersection of these two areas. So integral is defined for all x's which are real numbers such that x is strictly larger than 0. This is the area. This is a set of all real numbers. 0 is here, and the area in which our integral is defined is everything to the right of 0, excluding 0. Remember, that logical connector and which we have here, x cubed has to be defined and ln x has to be defined. Logical connector and, that corresponds to intersections in set theory. That is why we are using the intersection of these two areas. This interval here which we got is just an interval from 0 to positive infinity. It's an open interval. Now that we know our area in which the integral is defined, we are going to solve this integral. We are again going to use the integration by parts formula to solve it. We just need to find what are u and dv. So remember, we have an integral of u dv, and that is uv minus the integral of v du. This integral u dv is the integral which we had started from, this integral right here. We have that x cubed is algebraic. We have now ln of x, and ln of x is logarithmic. Our acronym is LIATE. L stands before A. So for u, we are going to pick L, logarithmic thing. So u is ln of x, and everything else that remains in our integral corresponds to dv. Ln of x is u, so x cubed dx remains, and that is our dv. Now we need to calculate what we need for this formula. We have u, we have dv, we need v. That is how we are going to calculate v as an integral of dv, which is an integral of x cubed dx, and that is x to the fourth power divided by 4. What is a differential respectful of u? That is a derivative of u respectful of the variable x multiplied by the differential of x. Ln of x derivative is 1 over x, and dx remains. So let's plug all of this information which we have into the integration by parts formula. The integral becomes u multiplied by v, and that is ln of x multiplied by x to the fourth power divided by 4 minus an integral v du. V is x to the fourth power divided by 4, and du is 1 over x dx. And now we just need to solve this. This is 1/4 of x to the fourth power ln x minus an integral. 1/4 is going to get in front of the sign of an integral as it is a constant. X to the fourth power is going to cancel out with x and remains x cubed dx. This is 1/4 of x to the 4th power ln x minus 1/4 multiplied by x to the 4th power divided by 4, and we have plus that real constant c at the end. So this is 1/4 x to the 4th power ln x minus 1/16 x to the 4th power and plus c, where c is a real number. And this is the final solution of the integral which we had started from. Let's solve the fifth integral on our list. That is an integral of x e to the power negative x now. We had x e to the power x. Now let's see what happens with this negative x. As always, the first thing that we have to do when solving an integral is to determine what is the area in which that integral is defined. X is defined for all real numbers, and e to the power of negative x is also defined for all x's which are real numbers. Intersection of these two sets is just a set of all real numbers, and that set is an area in which our integral is defined. Let's now integrate this integral using the method of integration by parts. We have x here, which is algebraic, and we have e to the power negative x, which is exponential. Remember the Lyate trick. A comes before e, and that is how we know what is u. U is x, and dv is e to the power negative x dx. Remember at this point, because we are using Lyate often, that is just an acronym. It's a mnemonic technique, nothing more than that. It is used so we can remember what we can use for u and what should be dv. This is not a mathematical rule, it is just a mnemonic technique. U is x, and that means that du is dx, and v is going to be an integral of e to the power negative x dx. To solve this, we are going to introduce a substitution that t is equal to negative x, and then differential of t is negative differential of x. dx is negative dt. So this is just an integral of e to the power t dt, and we have that minus sign in front of it. So this is just negative e to the power t, and when we return the substitution, this is negative e to the power negative x. So the integral which we have started from becomes u multiplied by v, that is x multiplied by e to the power negative x, and this minus sign here, minus an integral of v du. V is negative e to the power negative x, and du is just dx. This is equal to negative x e to the power of negative x, and we have already solved this integral here. It is negative e to the power negative x and plus c, which is a real constant. So finally, this is a solution of the integral which we had started from. Let's solve an integral number 6 on our list. 3x e to the power 2x dx. Again, this integral is well defined for all x's which are real numbers, as 3x is linear, that is defined for all real numbers, and e to the power of 2x, there is no problems in the area in which that is defined. So we have that area in which this integral is defined is the set of all real numbers. In the previous example, I have shown you what solving this type of integral looks like when you have negative x here in the exponent of e. You have to introduce a substitution in dv form to integrate it to v. If you want to avoid introducing that substitution in that step, you can introduce the substitution now in the beginning. So let's introduce that. Let's take that t is equal to 2x. differential of t is going to be 2 differentials of x, and the differential of x is then equal to dt over 2. Now this integral becomes 3 multiplied by an integral. X is t over 2, that is from the substitution, and we have multiplication by e to the power of 2x, which is t, and dx is dt over 2. So this integral is 3/4 of an integral t e to the power t dt. This variable t which appears in this integral is something that we call a dummy variable. We had an integral at the beginning, x e to the power x dx, and that was x e to the power x minus e to the power x and plus c, where that c was a real number. So if for the dummy variable x we put here dummy variable t, we are going to get the solution for this. So this is equal to 3/4 of t e to the power t minus e to the power t and plus that constant c. When we return our substitution that t is equal to 2x, we get 3/4 of 2x e to the power 2x minus e to the power 2x and plus a constant c, which is a real number. I just want to make one simple note here at this sign of the equation. You can ask at this point a legitimate question. Hey stupid, what did you do to that constant c? We have that 3/4 t e to the power t minus e to the power t plus c, and then is the closed bracket. Well, that is of course 3/4 t e to the power t minus e to the power t and then plus 3/4 of c. You have 3/4 of c, not just c as you wrote here. And to that I can respond with exactly you're right. But that c, as you recall, is a real number. If we say that c1 is equal to 3/4 of c, where this c is a real number, then 3/4 of c is again just a real number. It is a constant. So at this point, I am just going to get that this is 3/4 of t e to the power t minus e to the power t and plus some different constant c1, where c1 is just a real constant. That is exactly what I wrote. This c is any real constant. It will just swallow up any other real constant that you multiply it with. Let's now solve the next integral on our list, an integral of x squared minus 1 e to the power x dx. Let's first determine the area in which this integral is well defined. X squared minus 1 is well defined for all x's which are real numbers, and e to the power x is also well defined for all x's which are real numbers. And that means that the area in which this integral is defined is again an entire set of real numbers. We are again going to use the integration by parts method to solve this integral. We have the polynomial x squared minus 1, and that is algebraic. We have the next part e to the power x, and that is exponential. In our acronym LAYATE, as you recall, A comes before E, so algebraic is what we are going to pick to be our U. So U is going to be x squared minus 1, and dv is going to be everything else that remains under the sign of an integral. E to the power x dx it is. At this point we just need to calculate du and v. So differential of u is x squared minus 1, derivative of that respectful of the x variable multiplied by dx, and that is 2x dx. And v is an integral of dv, and that is e to the power x dx, which is just e to the power x. So this integral then becomes equal to u multiplied by v, that is x squared minus 1 multiplied by e to the power x, minus an integral of v du, and that is 2x e to the power x dx. This integral we are again going to use the same approach of integration by parts. In this integral, u is going to be x and the dv is going to be e to the power x dx. Explanation is the same as one that I just gave you. X is algebraic, e to the power x is exponential, algebraic is before exponential, and that is why we are picking u to be algebraic part. Let's calculate du, that is dx, and v is an integral of e to the power x dx, which is just e to the power x. So we have x squared minus 1 multiplied by e to the power x minus 2, and here we are going to apply the integration by parts formula on this integral. It is u multiplied by v, which is x e to the power x, minus an integral of v du, which is e to the power x dx. This is then equal to x squared minus 1 e to the power x minus 2x e to the power x, and plus 2 integral of e to the power x dx is just e to the power x. And of course, now that we have finished with all integrations, we are going to add that plus c, where c is any real number. As you can see here, we have e to the power x in common everywhere, so we can take that e to the power x, and what remains is x squared minus 1 from the first term, and then negative 2x from the second term, and plus 2 from the third term. And that is equal to e to the power x, x squared minus 2x, and minus 1 plus 2 is just 1 plus 1, and plus c. So this is then equal to x minus 1 squared e to the power x and plus c. Integral number 8 in our list was an integral of e to the power x sine x dx. In this integral, e to the power x is defined for all x's which are real numbers, and sine of x is also defined for all x's which are real numbers. And that gives us that the area in which this integral is well defined is an entire set of real numbers. We are going to use integration by parts again, and we have e to the power x, that is exponential, and we have sine of x, and that is trigonometrical. Layate trick, e is last, t is before e, so we are going to take that u is equal to sine of x, and dv is everything else that remains under the sign of an integral. Differential of u is then cosine x dx, and v is an integral of dv, which is e to the power x dx, and that is just e to the power x. The integral is then equal to u multiplied by v, that is e to the power x sine x, minus an integral of v du, and that is e to the power x cosine x dx. Now we have to solve this integral. Explanation is the same as before. U is going to be cosine of x, and the dv is going to be e to the power x dx. So du is going to be negative sine of x dx, and v is going to be e to the power x. So this is then equal to e to the power x sine of x minus, and we have this integral to be u multiplied by v, which is e to the power x cosine of x minus the integral of v du, and that is e to the power x sine of x dx, and this minus is going to get in front of the sign of an integral and give us this plus here. So this is then equal to e to the power x, and we have sine of x minus cosine of x in the brackets, as this e to the power x is in common, and we have minus an integral of e to the power x sine of x dx. This is the same integral which we have started from. So the question is, what happens and how do we solve this? We have just returned to the start. Well, the question now is, how do we get ourselves out of this mess? Clearly, nothing went wrong, but we can circle around to the infinity and back, and we are always going to get this one integral. So how do we solve this? Let's name our integral I e to the power x sine x dx. As you can see, we have that integral, so I is equal to, and we have here e to the power x sine x minus cosine of x, and minus again that integral I. When a negative I comes on the left side of the equation, it becomes plus I, so we have 2I e to the power x sine x minus cosine of x, and then I becomes 1/2 e to the power x sine x minus cosine x. I is an integral of e to the power x sine x dx, and that is equal to 1/2 e to the power x sine x minus cosine x. And again, we are done with integration, so plus c, where c is a real number. What do you say? A neat little trick. An integral number 9 on our list is an integral of ln x dx. Well, always the first thing is to find the area in which the integral is defined. Ln function is defined for all x's which are strictly larger than 0. That means that the area in which our integral is defined is an open set from 0 to positive infinity. Number 0 is not included in that set. Now, the integral which we have is interesting because we have only one term in the integrand, and that is ln of x. Here also you can use integration by parts. This part right here, dx, you can see that as 1 multiplied by dx. And that is an algebraic term. And you have ln of x, which is a logarithmic term. So here again we can use Lyate. We have ln of x, which is logarithmic. We have 1, which is algebraic. In Lyate, logarithmic comes before algebraic, so u is going to be a logarithmic part. That is ln of x, and dv is everything else inside the integrand that remains. So that is just dx. Differential of u is 1 over x dx, and v is an integral of dx, which is just x. We are going to use the integration by parts formula, and that is u multiplied by v, x ln of x, minus an integral of v multiplied by du, that is x multiplied by 1 over x dx. So this is x ln of x minus x, and 1 over x are going to cancel out, and we have an integral of dx. So this is equal to x ln of x minus x, and plus some real number c. Integral number 10 on our list is an arcus sine of x dx. The area in which the function arcus sine of x is defined is for all x's which are real numbers from the interval of negative 1 to 1, where these numbers negative 1 and 1, borders of that interval are included. Therefore, the area in which this integral is defined is negative 1 to 1 closed interval. Here again we have only one term in the integrand, and that is arcus sine of x, which is inverse trigonometric. Again, dx we can look at as 1 multiplied by dx, and 1 is algebraic. In Lyate trick, inverse trigonometric comes before algebraic, so we are going to pick for u to be this inverse trigonometric function, arcus sine of x, and dv is everything else that remains in the integrand, which is just dx. Differential of u is equal to 1 over the square root of 1 minus x squared, and v is an integral of dv, which is just going to be dx, and that is x when we integrate it. So this integral is then equal to u multiplied by v, that is x arcus sine of x, minus an integral of v du, that is x over a square root of 1 minus x squared dx. The question now is, how do we solve this integral? And we can solve it by using the substitution that t is equal to a square root of 1 minus x squared. dt is then going to be 1 over 2 square roots of 1 minus x squared, multiplied by the derivative of this, which is going to give us negative 2x, and dx at the end. So this is just minus x over a square root of 1 minus x squared dx. So this is equal to x arcus sine of x minus x over a square root and multiplied by the dx is just dt. So we have plus an integral of dt. So this is x arcus sine of x plus t and plus a constant c. And when we return the substitution, this is plus a square root of 1 minus x squared and plus c, and this c is a real number. Lastly, I want to show you how to derive this formula for integration by parts. We have this product here, u multiplied by v, and let's observe that product when we take the derivative of it. So we get the derivative of u multiplied by v plus u multiplied by the derivative of v. When we take a differential of u multiplied by v, we get v multiplied by du plus u multiplied by dv. This u dv is then equal to differential of uv minus u multiplied by dv. And now we are going to integrate everything. We have an integral of u dv to be equal to an integral of the differential of uv minus u multiplied by dv. This is equal to an integral of the differential of uv minus an integral of u dv. So this is just uv, as integral of the differential of uv is uv, minus an integral of u dv. What have we gotten? Integral of u dv is equal to uv minus an integral of u dv. And this is the formula for integration by parts. Just a little reminder here. I have already made quite a few videos on integration here on the channel, so I would recommend to you to check out this playlist of integrals linked in the description, which I have solved here, and try some of them for yourself. Please subscribe to the channel, like and share, as that support helps me a lot. If you would like me to cover a specific topic, write about it in the comments and I'll see you in the next video.